All right, guys, let's dive in here. You knew they were coming. We've got our special cases for systems of equations, just like we had those special cases when we were solving our equations. Let's look at what they look like, how they come up, and how you guys solve them. All right, so remember back when we're solving equations, you guys were given a problem like this. We would have a variable on both sides. We want to get rid of that to move all the variables to one side. So I'm going to move all my variables to the left. And I'm going to, at the same time, then move all my constants to the right so that everything's on only one side. I end up with -7 over there. And, no x's over here, which means I have 0 left on the left. And I have this as my final equation. And what does that tell us? You're right. That's a no solution. Okay, so when we're solving equations, we end up with a no solution anytime we end up with an equation that we find is untrue. It's a false statement. It's exactly just like solving equations from your past unit. You just solve for the variable cancels, and you're left with that false equation where your variables disappeared. So we see we're in that exact same boat. The same idea presents itself in our systems problems. If we look over here on the left, problem number 1, what's your solution? That's probably pretty obvious. You guys are getting that by now. It's right there. X value of 1, then Y value of 1. A lot of you guys, by the way, are missing that on the quiz this last week. You have to have your X value first when you write a point, and your Y value second. Lots of folks are getting those backwards. All right, so that's pretty obvious. What about number 2? What's our solution on system number 2? I don't know. Let's look a little closer. We see that 1, 2, 3 over 1 is that first equation, which means it has a slope, 1m, of 3. And if we look at the second equation, 1, 2, 3 up, and over 1 also, which means that guy also has a slope of 3. We have 2 lines with a slope of 3. If you guys remember what that means, it tells us these 2 lines are parallel. And I think there's only one R in parallel. When you have 2 parallel lines, that means they're never going to meet, they're never going to cross. And if our lines don't cross, that means there is no point or no solution where they're ever going to cross. So we can see if a system of equations makes lines, and we have 2 of them that are made into lines. If we run 2 parallel lines, by definition, they'll never cross, which means we can't get a solution point. We can't find an XY that's on both lines. There is no point on both lines. Okay, so that's called a no solution system. And what that means is just what we said. A no solution system is a system without an XY that solves both equations. Or is on both lines, however you want to look at it. If we're talking about the 2 equations as graph lines, there won't be a point where they both cross. If we look at them as equations, there won't be an X and Y value that makes both of them true. Okay, so looking here, graphing to solve, here's a great example with this system right here. We've got a -1/3 x starting at +4. So if I went up 4 and then went down 1 over 3 and had a line like this, and my second line was starting at -2 but also going down 1 over 3, I'm going to end up with two parallel lines that never cross and go forever right next to each other. Okay, so that's what it looks like in terms of lines. If I'm looking at it over here as a system, let's just solve this, and I'm going to use elimination. I'm going to go to make an opposite pair out of these x's right here, which means I'm going to multiply this top equation by 2 and make it -2 so that everything cancels. So then I'm going to get a negative 6x, then a positive 8y, and then a negative 16. So notice I just multiplied that top equation for right here. And when I add, my x's cancel just like I wanted them to, but so do my y's. They're both opposite pairs. I went from no opposite pairs to when I created one opposite pair, I got both. Everything cancels. 0 is all I have left on the left side of the equation. And then I get -6 over here. And what we see is a false equation, which means a no solution. So we see that when we work through these equations as algebra, it's exactly, if we were to jump back, even with a system. So it's really not anything new. You do what you already know. And when you encounter that no variable situation because they disappear, you know you already know a solution. If you see it on a graph, you've got parallel lines and they'll never cross. By the way, random fact, during your lifetime, you will create enough saliva to fill 2 swimming pools. Oh my gosh, that's disgusting. Okay, let's keep going. Hope you're still with me. Here's another type of special case. There's line number 1 in the system. We graphed it right there. And where's the other line? Well, it turns out that's the other line as well. If we were to zoom in really close, we're going to see 2 lines running right on top of each other. That's the third way you can have 2 lines graphed in a plane. If you think about it, they either have to cross like that. Okay, that's option number 1. You can have option number 2, where they run parallel to each other. Or you can have option number 3, where if that's line number 1, that's line number 2 going right over the top. All sets of lines have to be one of those 3. We've learned with number 1 how to find the solution. That's our normal case. It's the point where they cross. Number 2 we just saw is a no solution because they run parallel forever. And the third possible case is called an infinite solution, which we've also already heard of because now every single point on both of those lines is on both of those lines. So the x and y of every point you see on that line will make both equations true. Just do. There we go. Okay, infinite solutions. What does that look like? Well, I just showed you on the last page. If you're graphing, really, notice guys, before you even graph, it's the exact same thing. If you take an equation and you graph it, the only way it can be written is slope-intercept. And if it's the exact same line, it's going to have to be in the exact same form. So it's going to be the same line graphed twice, really obvious. We don't even have to graph it. If we're substituting or eliminating, let's see how that works. I'm going to rewrite that top equation. I'll use some substitution this time. I'll move that 4x over and make it negative. And then I'll just flip all these terms to make it a positive y that I solve for. And I'm just going to rewrite the bottom equation and substitute in for that y. Okay, so hopefully you're tracking with me. I'm even going to make it a little bit easier. If not, because hey, it was a weekend. There we go. We just substituted out the y and substituted in that value. We'll distribute. And I bet you already see what's going to happen. right here, when I combine my like terms, 8x and negative 8x, they just combine together, good guys, bad guys. But there's nothing left once they do. All I'm left with is that negative 12 on the left, that negative 12 on the right, and there's our other special case, which you've already seen before. It's a true equation, therefore, it's an infinite solution. So again, what that's telling us is it doesn't matter what x and y value you plug into this equation, it's going to be true because these x's all cancel out anyway. The y's all canceled out because we use substitution. And so no matter what number we use, we're going to end up with a true statement of negative 12 equals negative 12. So it doesn't matter. And that's as if we were to graph lines. 3x minus 2. It's two lines right over the top of each other. So that's the same idea. All these points are in common. All those xy pairs make them true. And what? And that was an extra slide. Let's practice looking for. All right. So if we're going to work through these systems, notice, guys, that you can work through them the normal way, but you can identify the shortcut as well. So for instance, if I'm going to work through this example, I'm going to probably go with elimination. And so first thing you want to do is move things around. So I'm going to move my x term over here, and I'm going to move that constant over so they match the top equation. So that'll be negative 10x, and I move it left, plus 14y, and then I'll move that 18 over, make him negative 18. Now I'll just see if I can grab that equation and move him down, which it lets me, good. And I'll move him up out of the way. Now, I can look at this and say, well, I'm just going to multiply this equation by 2 to double it up, and a negative, so that they'll all be opposites. But do you notice something right here before we even go any further? If I double the top equation, they're both going to become negative 10x. If I double the top equation, they're both going to become a 14y. That right there tells me that's a special case. As soon as you see that, keep solving if you need to. And even if you don't see that ahead of time, it's okay. Keep solving and it'll show you. But that tells us right now we've got a special case line, okay? How we know the difference is whether or not the constants end up matching, okay? And we can look here as well. The negative 2 times, or excuse me, we were just multiplying a 2 so far. The 2 times the negative 9 also matches as a negative 18. If everything matches, I'm going to have an infinite solution in a minute. And I can see that because all they really did was take negative 5x plus 7y equals negative 9, and then they just doubled everything to make the other equation in the system. They made a negative 10x, which is 2 times that, a 14y, which is 2 times that, and a negative 18, which is 2 times that. They just used your fraction buster trick against you. They double one equation to make it the other, and there's that infinite system, okay? So if you can, feel free to identify it that way. If you need to work through it and see the variables disappear, by all means do that. Why don't you take a minute and look at this second one? Either A, look and find if it's special case by seeing if they're just multiples of each other, or B, just work and solve it out, and if the variables disappear, you also find what you need to know. Try it. All right, I'm going to do this both ways just in case people could use both to look at. I'm going to look at this right now, and if I want to use elimination, I'm going to move this guy over and make him positive 3y. And I'm going to move the negative 24 to the other side and make him positive 24, so it matches the top, and leave that 9x. Now, just between those two, I would look at those two equations and say, the negative 3 becoming a 9 is just a multiple of negative 3. the negative y to positive 3, also a multiple of negative 3. That right there tells me I'm in a special case. The x and the y terms are identical. Now remember, guys, when I say identical, it's because you can multiply something through the whole equation. So now, whether it's a no solution or infinite solution, is just whether or not these constants match. If they match, that means that it's going to be a true statement equation if I solve it out. If they don't, then it's not, and it's a no solution. Is that a multiple of negative 3? Yes, it is. So that tells me this is an infinite solution. It's the exact same equation. It's just all multiples of negative 3. Now, if you didn't see that or you weren't tracking with me fully, totally okay. You can just solve it the way you know how, and it will automatically reveal to you what it is. Okay? Notice here, I'll just move that guy over so that I can just use substitution. So I'll cancel, and flip his sign to negative. And now I'll have the y equals 8 minus 3x, and I'll just plug that in right there. So now I'm just using my regular substitution method, no need to be looking for or seeing the special case ahead of time. I'll just do my regular math. Negative 24 plus 9x. And you guys see what's going on. Even at this point, it starts showing you. There's a negative 24 on both sides. There's a 9x on both sides. It's showing us it's going to be an infinite solution equation. When I add over the 24, both sides end up canceling. When I minus off the 9x, both sides end up canceling. And I end up with 0 equals 0 is all I have left. And that's a true statement, which tells me I've got an infinite solution. Okay, there you guys go. If you want the shortcut, there's the shortcut method, okay, right here. You'll always have the x and y terms identical. They just will try to dress them up. It's just whether or not you can see it in these types of examples with your equation solving and skills to rewrite and multiply through things. But if not, you can always solve like usual. All right, here's your homework. Damn it. Here's homework. Got 3 problems here. Solve each system and identify if it's a special case, and if so, which it is, or else tell me what the solution is. I'll work through these 3 after you to give you the solutions. Go. Pause it now and unpause it at the end. All right, let's dive in, guys. I'm going to just solve both of these for y to use substitution. That looks really easy, so I'll move that 3x over here. I'll move that 6x over here. Now they're both negative y, so I'll flip the signs all through the top equation, flip the signs all through the bottom. Wow, they were all negative. And now I've got 2 equations solved for y. Now I can look at them right now, and I see it's not a special case solution. I can tell that because the y terms have the same coefficient, but the x's do not. So if I were to multiply through the top equation to make the x's match, then the y's would no longer match. So they're not something I can make match up. They're not both a multiple of the other. One of them matches now, one of them would need a multiple to match. So I know I've just got a regular problem to work through. I'm going to go ahead and just set them equal to each other and use my substitution. So on the top equation, I've got the 18 plus 3x equals the y of the other one, which is 27 plus 6x. And I'll just solve like normal. Take 3x off, and then I'll take 27 off on the right to move it over. It's going to be negative 9. Dividing off that 3 tells me the x equals negative 3. I'm halfway home, and I'll plug in to the top equation 3x, which is 3 times negative 3 when I plug in. Now we've got 18 minus 9, which is 9, so y equals 9. And we've got negative 3 comma 9, and there's my solution. That's regular. All right, let's do number 2. I'm going to write those in the same form so they look the same. So I'll move the 3y over to the left and flip its sign. I'm going to move the x over there to the other side and make it negative. Okay, I'm just putting everything in the same form, and then I'm just going to copy down this equation. Y equals negative 4x plus 8. Now at that point, I'm going to use elimination. So I'm going to look at the 2 and say, if I want to make opposite pairs of the y's, I'm going to multiply that bottom equation by 3. And I want them to be negatives, so I'm going to use negative 3. So I'm going to get negative 3y, positive 12x, and minus 24. And now I'm going to, I can't move that guy. I'm going to be combining this top equation and this one that I just rewrote using that multiple. And probably you've already noticed or already did it ahead of me. I've got a cancellation there of an opposite pair and a cancellation there of an opposite pair. So I've got 0 equals. Oh, and look at that, another opposite pair. 0 equals 0, true statement, infinite solution. You might have seen that ahead of me. I didn't jump to the shortcut version on that one, but you could have just noticed they were multiples of each other. These two equations were just multiples. One was a multiple of the other, and that's an infinite solution. The last one. I'm just going to jump right to it. I've got it already solved for x, so I'm just going to use substitution. It's kind of set up for that. And as soon as I do that, I get this. And you see that I've got a negative 33 and a positive 33. So when I combine those like terms, they're just going to cancel. Now all I'm left with is negative 15y equals negative 15y. Now we could see right now that that's a true equation. And it's an infinite solution. Or you could keep going. Try to move all the y's over to one side. See that they all cancel, and now you're at 0 equals 0. Either way, it's true, and it's another infinite solution. All right, there you go, guys. See ya.